Hi everyone. Today we're gonna do our second LS-Dyna tutorial. So in this tutorial we're gonna do a simple the simulation of a simple tensile test. So instead of making the specimen using LS Prepost, this time we're gonna have an IGS file and try to import it to the Prepost. So the file that we're gonna use is actually this file. Okay, and you can download this file from here. Okay, this website, the GrabCAD website. I think most of you guys know it. And this is my account, so this is the specimen that we're gonna use. You click here to download, and most importantly, by the way, this handsome guy is myself. Okay, so when you download it, you will have this file. Okay, so now we're gonna import this one. So how we do that? You open the Prepost file, import, and IGS file, or you just click on the shortcut Control G. Okay, you have this one, click and open. Okay, now you have several options. You just click on this one, specify unit, which is mm. We're gonna work with millimeters. Click OK, and this is your specimen. Okay, so if you rotate, okay, control and the left mouse button to rotate, you can see it is a 3D model. So actually you can mesh the 3D using this one, solid mesher. But if you use this one, you will have a solid elements, and of course solid elements, more nodes, and it will take longer time to run the simulation. So instead of this one, we use auto mesher, and we only mesh this surface. We mesh this surface as shell, then we define the thickness of the shell to be the same thickness as this one. Okay, so you click here, compute. You see the size here is 1.78, and you can see here is the mesh, and I think the elements are a bit too big. Okay, so you can keep it like that, click on accept, but for me I prefer it to be 0.5. It will be smaller, the simulation will take longer, but it's okay, my PC can handle it. So reject and mesh again, so you have a very small and nice mesh. Accept. Okay, so now we're done making our specimen. Okay, so here you have you go to the corner here, you have shape group and FEM parts. Okay, so on the shape group, you can see if you click here, the IGS solid will disappear and appear. Okay, so right click here, and you can actually hide it or show it, or you can straight away just delete it. So really remove selected shape. Yeah, really remove them. Okay, so now we have this one. So as we said, this is a shell, but we want it to be have a thickness equal to or more or less the same as the thickness of the specimen. So to do that, I go to keyword manager and click on all to show all the keywords. Select on section and shell. Okay, new ID, title optional. If you want to put it, fine. If you don't want, no problem. Shell section. Okay, this one, default. This one, shear factor. They say suggested value is 5/6, which is 0.83333. And the thickness, this is the important thing. Okay, let's say I'll just put it as 2 millimeters, and click on enter, and then click on accept. Okay, now we have done defining the section. Now we want to define the material. Okay, defining the material gonna be a bit different from our previous tutorial format. Here we have, in the previous tutorial we used power law plasticity, but now we're gonna use this number 24. Okay, piecewise linear plasticity. So this is the things that I need to key in. And let's say this specimen, I want it to be aluminum, any type of aluminum. Okay, so where to get these values? Actually, you can find it on the internet, in the literature, in some of the papers, but here I prefer to use this website. Okay, this website, environmental's engineering page. Okay, why? Because the materials are available here are in different units and also with different material models. So you scroll down, more down, you can see here material number 18, power law plasticity, which we used last time. So you can see here include for all 1044 materials. So meaning if you download this one, it will have the database for 1044 materials, and also in 5 systems of units. So we said we're gonna use material power law plasticity, which is 24, and this is 24, but here you see material all, no failure. So in this case, no matter how much we pull the specimens, in this case, no matter how much we pull the specimen, it will not fail. So I want something with failure strain or failure criteria, and here I have this one. Okay, so this one met all. You download it and you unzip it, and you will have 5 files. Okay, each file in one of the systems. Okay, so you will have 5 files, and you just select this one. Okay, in this file you'll see the units: kilogram, millimeter, milliseconds, kilonewton, gigapascal, and kilonewton millimeter. Okay, so the first material is aluminum pure 99.996 annealed. We don't want to use this one. We want to use different material. Okay, so this is hanging. It's taking some time because the file is very big. Okay, so you will have all the things that you need here. Okay, but for this one, let's say we'll use the second one. Okay, aluminum pure 99.49. Okay, so I have these are the things that I need to copy and paste it here. Okay, so first I have the density. Copy and put new ID and paste it here. Then this guy, copy, paste it here. Poisson's ratio 0.33, and then I take this one, sigma yield, copy and paste it here. Tangent modulus 0, and failure plastic strain, this is important, is 0.2723. 0.2723, and here I put the title. I just copy paste from here because I'm a lazy guy. Okay, and click on accept. But now the definition is almost complete, but not actually complete, because if you go down here, you have define curve. What is define curve? What is this curve? This is the curve actually for the stress strain. This is the points for the stress strain relationship for this material. So here I need to define a curve using LS-Dyna. So here I just accept for the time being and go up, find define and curve. Okay, so add. This will be stress strain curve for the aluminum that we're gonna use. Okay, so here actually we can input the data one by one. Okay, here and here, here and here, one by one. But actually you can just load here, load x y data if you have the points on separate file. So what we do here, I click Control Shift and I delete everything before the curve. Scroll down, I put the cursor here, Control Shift and end. and I delete. So now I have this file have only the stress strain points for the for the material. So here I save as here. Of course I need to change the format. Stress strain format gonna be .csv. Save. Okay, I see here I have this is the one that we just made it. So open the Prepost, load XY data. I have now the files, the points. Open and accept, and it's ready here. Okay, so now we have the curve. Now we need just to link it to the material. Scroll down, go to the material again. Here we're gonna put it here. Okay, load curve ID, load curve defining effective stress versus effective plastic strain. Click on this dot and you have the curve that you just defined, and click on done. Accept. Done. Okay, so we finish defining the material. Now we're gonna link the material and the shell, the material and the section to this part. So click here, part. I didn't name it yet. I say specimen. Section ID, I have only one section, shell section, thickness is 2 mm, and the material model is this one just now, and click on accept. Okay, alright, now the boundary condition. Click on the top view here. Okay, we have to fix one side and pull the other side. So how to do that? First I'm gonna make two set of nodes, this nodes and these nodes. So click here, create entity, set data, and go to set of nodes. Okay, create. Alright, this one we're gonna name it fix nodes. Okay, here this small window, it shows you how you can select your nodes. So I go select by edge and propagate, and click on one of these edges and the selection will propagate, and click on apply. Okay, now I create again the second part, the second set of nodes. Okay, now I'm gonna use different method of selection by node and area, and then I make this area and all the nodes are selected. Now before I hit the apply, I name it moving nodes and click on apply. Okay, so now we have the two set of node. Okay, it's showing both of them. Okay, this is the fixed node, this is the moving nodes. Okay, none. I hide both of them. Okay, cancel, close this one, open the keyword manager again. Now first I want to fix one the left side. So to do that, I go to boundary, SPC set, double click here, new ID, then here I say fixing nodes. Okay, node set ID, click on this button. I have the two sets. I click fix nodes and done. Okay, this one is the degree of freedom, translational in 3 axis, and this is the rotational. So these nodes gonna be fixed in 3 directions and also cannot rotate around the 3 axes, and accept. Done. Okay, so now we're gonna define the movement of this one. How to do that? From boundary also, boundary prescribe motion set from here. Okay, but here as you notice we need LCID. We need a curve that defines the velocity, the displacement, or the acceleration of the nodes that we want them to move. So again, I go down to define. We go to this guy again, define and curve again. Okay, so now I click on add and say I want to input the velocity of the nodes that we're gonna put. I mean the velocity of the tensile test. Velocity. Okay, so let's say the velocity is 0.5 meter per second or millimeter per millisecond, and then I click on insert. Of course I need another point here. Let's say I put a very big number, let's say 1000, and again insert, click on accept. Now if you plot, this is the profile of the velocity. So the velocity gonna be constant and it is 0.5. okay, this big number should be bigger than the total running simulation. I mean the total should be bigger than the termination time. So if your termination is let's say 2000, then let's say you make this one 5000 or 10,000. Now you close this one and done. You go up again to prescribe motion set. Okay, add, click on add, then here you say moving nodes, set of nodes, set of nodes. You click on the moving nodes, which is actually on the right side if you look from the top view, as we are doing right now. This one we're gonna pull them. Okay, degree of freedom 1, of course, because we're gonna move them in the x direction. Okay, VAD, velocity, acceleration, displacement. Okay, the curve that we did just now is for velocity, so we just make it equal to 0, don't change it. Now the load curve ID, we click on velocity and accept. Okay, done. Okay, now we have actually one more thing. These nodes, we want them to be fixed in the x and y, in the y and z. We want them only to move in the x direction. So to do that, again we go here. Okay, this one I click on new ID. Okay, here fixing moving nodes. Of course it's gonna be in the second set of nodes, and we're gonna only allow them to move in the x direction, and then click on accept. Okay, so the remaining are only very few small things that you already know. So the output, how to define it, here we have many things. Now we're gonna do binary D3 plot. In the this dt, the time interval gonna be 1 millisecond, ms, not mm. Okay, then the control termination, this is the last thing. Control termination is down here, gonna be 35 millisecond, and accept. Okay, so I think that's all. So now you will save the file. Okay, Control S to save, or from here save as, keyword manager, and you browse. Here remember you save as K file. So here I just say, let's say tensile test.k, or no need for the .k if you are using the latest Prepost. Save and save. Okay, now you open this, you have this file. So you go down here, you open the manager, the LS-Dyna manager, you run the simulation. This one, click this the file that we just did, open, and here I put 8. This one I put 3 and 0 0 0 0 0 0 0 0. This one depends on your PC. Okay, it says 24 minutes. Okay, so we will not wait 24 minutes because we actually have the results. I actually have the result. You don't have. You have to wait. I don't have to wait. Okay, this is the D3 plot. So you pull this guy and drop it here. Okay, either one of them fine. I have two versions of this one, so let's try the latest one that I have. Okay, so this is the result. If you click here play, he is gonna be pulled and become thinner and until it breaks here. Okay, so here from this one you can see many results. Okay, from the post processing you can, let's say this, you want to see the plastic strain, effective plastic strain. Okay, from beginning you play, you can see the plastic strain, and the value here is 1 point, now it's 2, 2.5, 2.6. maybe it's not clear to you. Okay, then okay, all these things you already know. I mean, you have many options here, you can choose whatever you like from them. Okay, now we're gonna try something new. History. Instead of part we say element. Now let's say we want to plot the results of one element. Okay, so effective plastic strain of, I randomly choose this one and then plot. Okay, so this is actually the plastic strain. This is the plastic strain and this is the time. So I save, and this one you have to put it as CSV file. So I say plastic strain.csv, CSV, save. Okay, done. Now for the same element we're gonna try to plot the effective stress, von Mises stress. So plot. Now you have this stress going up, and here is going down because at this time the rupture happened in the specimen. So again I click on save. Remember to choose the output file, this one, Microsoft CSV file, single axis. Now instead of this one I say, hey, what happened? Sorry, I say, I click on Windows button by mistake. Here I say stress or von Mises equivalent stress and click on save. This is the stress versus time. So now I will, let's say, open here. I have the plastic strain and the stress. I have the plastic strain, yes, and the von Mises stress. Okay, these two files, and if you open them you will see like this. Okay, XY, this is the X and Y. Actually, depending on your Microsoft Excel, if you have the latest, I think it will separately put this one in one row or one column, and this one also in one column, so you straight away can plot the result. But because my Microsoft Excel is not that updated, so we right click, open with Microsoft Notepad or WordPad, and here I say Control and H to replace. So this comma I replace it with semicolon and replace all. So I have the semicolon here. Click on save. Okay, I saved it. So now you can see it is separated. Ta-da! Okay, so we're gonna do the same thing for the second one. Open with Notepad or WordPad, Control H, and instead of comma I put it semicolon and replace all. Okay, and Control S to save. Now you close that. So here you have the von Mises. This is the time and this is the value of the von Mises stress, and here you have time and you have strain. So let's say I want to plot the stress and strain. Okay, so this one, copy the stress, I copy here and I paste here. Okay, so this one I think I don't need it, delete. Here I highlight both of them, insert. I prefer this scattered one, and here you have the stress and strain. Okay, here I say stress versus strain, or to be more specific, von Mises stress versus equivalent plastic strain. Okay, now all these things actually in Excel have nothing to do with LS-Dyna. Just to make it nicer, here you should put that of course you should put something and label it. Here axis title, here you say strain, and strain millimeter over millimeter, and this one you put stress rotated vertical. No, not this one. Yeah, rotated. You say stress, and remember we used the units, the system of units, that the stress in gigapascal. So this guy also, these values also are in gigapascal. Okay, so now you have this one. Okay, so that's all for the second tutorial. Thank you very much. If you like, please subscribe, share. You have any requests or questions, you can put it down in the comments. Okay, thank you again, and bye bye.